And higher order polynomial, it's not desirable. Yeah, the higher the order, the more complex the model is. So we strive to get low order model. And if you have, if you have some points, you can fit a straight line. Or if you have, let's say, a loop, then you can fit a quadratic curve. And if you have data of this form, you can then fit a cubic equation. So if you have this, then it will be fourth order polynomial. So let's look at this data set here. If we are not going to use spline, just use what we learned about multiple linear regression, what would be the order of this polynomial? So you just count one maximum there, so order 2, order 3, 4, 5, 6, 7, 8. So to fit a polynomial that is suitable for this data set, we need order 8, which is a very complicated model. And it comes, and along with it comes a problem of multicollinearity, dependence of the regressor variables. So, so this spline is a way to fit low order polynomial at different segments and then combine them together. So in this example, I decide to choose my two knots at T1 and T2 because the behavior of the points are different in these three segments. That's how I choose. See here, suddenly it goes up. So here I can fit a cubic model, here another cubic model, and then here another cubic model. So, well, a very naive way of doing things would be, we now know that we want to fit a cubic polynomial in each segment, 1, 2, 3. So a naive way of doing things is use the data up to T1, fit a cubic polynomial. Use the data between T1 and T2, discard everything else, fit a third order cubic polynomial here. And same thing for the last segment. Use the data from T2 onwards, fit a cubic polynomial. And then that will be answered. Yeah, that's a naive way of doing things. One drawback of this approach is that after you fitted 3 cubic polynomial, and suppose I want these 3 polynomials to be continuous at the 2 knots, will that happen or not with this naive approach? Just fit one here, fit one there, and then there. That's, I tell you, it's highly unlikely the 3 cubic polynomials that you fitted will be continuous at the 2 knots. Because they are done separately. Why should they be continuous at the 2 knots? Yeah. So this naive approach is not going to work. Okay? So, let me state my objective clearly. I want to fit 3 polynomials in the 3 segments such that they are continuous at the knot. That's my criteria. Okay? So how do we do that? Well, turns out that it is not that hard. So let's look at this example, okay, with 2 knots. Let's just, I explained this notation, but today you'll be clear why we need such a notation. So I've gone through these 2 pages. Let's come to this example. So I have 3 segments. One segment here, one segment here, the first segment, and then the second segment, the middle segment, and the third segment. Okay. All right. For the first segment, what do we want? We want a cubic polynomial. So that would be our equation. Sx is beta naught plus beta 1, beta 2, beta 3. So you can see it's a cubic polynomial. All right? And for the middle segment, we will continue to use this basic, this polynomial, cubic polynomial from here. And what we do is, we add another cubic polynomial. When you expand this, you have a cubic polynomial, of order 3. You will have all the terms of x, x squared, x naught, x squared, and x cubed. So you can see that the first segment, we have a cubic polynomial. In the second segment, we also have a cubic polynomial. This polynomial is different from this because we have added another cubic polynomial. Of course, these 2 will combine together to form a new cubic polynomial. Is that clear? So, we have a cubic polynomial. We want a different cubic polynomial. We don't know what it is. Let the data decide what for us. So we just add a cubic polynomial here. Same thing for the third segment. We will continue to use this base, this polynomial for the middle segment here. And then add on another cubic polynomial. So in effect, we have 1 cubic polynomial here, 1 cubic polynomial here, and 1 here. And they are all different. Okay, that's easy. So we have defined cubic polynomial for the 3 segments. So now let's turn to continuity of the spline model. Spline means the whole thing. So how do we ensure that these 2 polynomials are continuous at the first node T1? So how do we ensure that? Remember my objective. My objective is to fit a cubic polynomial that is continuous at all the nodes. So I have defined a polynomial here. I have defined a polynomial in the second segment or the middle segment. How do I ensure that these 2 are continuous at T1? In fact, if you look carefully now at this polynomial, when x is near T1, what happened to this? When x is near T1, this part will become what? 0, right? So, if you approach T1 from the right-hand side of T1, this polynomial will approach this. At T1, at T1, you can substitute T1 into here. But the way I define this cubic polynomial here is that I notice that if I let x goes to T1, this part will be 0. And so you can see that these two are identical at T1. And so they are. And so these two polynomials are in fact continuous at T1. You see that? That is how I define two polynomials that are continuous. Now, so what do I know here? Well, I know that I need to have beta 1 here and 0 here. That's what it is. I mean, if I want to try to combine these two models, I notice that I need a beta 1 here times 0. Okay? And these two so how do we represent these two? To represent these two, we need this plus notation. Plus. That's why this notation, the plus notation comes in. If you have x less than T1, this quantity here will be 0. And if you have x greater than T1, the one that I shaded there is this one. So, if I use that notation, I would have defined the same model over these two segments. Can you see that? That's why we need this notation. Okay? Next, let's go on to this. Now, how do I ensure? Now, if you look at the polynomial here and the polynomial here, are they continuous at the point T2? They are. Because up to T2, you will have this, just a base model. But when x approaches T2 from the right hand side, this will become 0. So if I define my cubic polynomial here, I ensure that these two polynomials are together is continuous at T2. So in other words, I actually need, so this one, I actually need beta 2 times 0 cube. This one I need beta 1 times 0 cube. Or just 0, I don't need this, okay? So, to represent this whole thing, I will just use this one. So if I write my model this way, I'm actually writing the three models here. Can you get that? So this explains why we need the plus notation. If you understand that, you understand spline model. So, I've explained, the T notation, the plus notation here. So for x less than T1, this is 0, this is 0. But for x between T1 and T2, this is x minus T1, this is 0. and the last one. Okay, so we now have one equation to represent the whole model. And means 1. So what that means is a spline model can be expressed as one multiple linear regression model. Because we need 0, for x less than t1, and for x between t1 and t2, we need another 0 here. That's why we need the plus notation. Nonetheless, this is one equation. This is one multiple linear regression model. And because it is one multiple linear regression model, we can fit this model. We can fit this model, and then we can test whether beta 1 is 0 or not, beta 2 is 0 or not. Suppose I want to test beta 2 and beta 1. Are they 0 or not? That means I'm trying to see whether a cubic equation is good enough for the entire data set or not. Or do I need different cubic models for different segments? So, this is very important, this note here. It says a spline model over several regions separated by the knots can be fitted as a multiple linear regression model. So let's come back to this model with 2 knots. And I am going to have my base model here. This is my base model, or the model for the first segment, this one here. And then, depending on the number of knots, I will introduce further quadratic polynomial to be added up. So, if I have 2 knots, then the addition of these will be the cubic polynomial for the middle segment. And the whole thing will be the cubic polynomial for the last segment. Because of the plus notation, what that means is if x is less than t1, these 2 will be 0. That's why we only have this model. And for x between t1 and t2, x greater than t1, then this is positive now. You take it as this. And if your x is greater than t2, then these two terms are not 0. They are cubic term. Okay? So that's what it is. So when you fit this model, what happened to this blank page? Strange. Get rid of it. I think there's a ghost in this room now. It's trying to block my view, or your view. Okay, let me get out. Let me reload. See that, the ghost. What can I do? Okay, let me try something else. I'm not sure what happened. I think there's a ghost running loose. Let me try and get rid of it. Oh, I else have to reboot. give a bit of time to get over this. I think everything hangs now. Oop. And it will move now. Let me try and reboot my computer.
The value of the derivative this is like it's product is one and then double is just one. So this for these two edges and X like it's one like this. So then if it's resistant to 0, then it's searchable like this. Feel it like that.
Okay, it's all right. I have a backup. So, I don't know what happened here. Let it take a break. So what happened here is, am I here? Yeah. All right. So what I have here, the equation in the box describes the spline model, and it can be written as 3 separate models for the 3 segments. So when I fit the model, it will look something like this. So this first segment is the base model, and the second segment here can be described by the addition of a cubic component. And then the third segment, I have another cubic component added right here. And the way I define this model is that they'll be forced to be continuous at the 2 nodes. So that's what we have. Yeah. Now, if you force your polynomial to coincide at the nodes, you're going to give up something. The fit in the middle segment, and this segment might be affected. If you relax this condition, say you allow discontinuity, then you will get better fitted model. So let's look at this voltage drop data. Okay? And so I have the time here, the voltage. So there are two variables here. And voltage is my response variable, and time is the explanatory variable. So here's a plot of the data right here. And if you look at this plot, it looks like what? There's one loop here, 1, 2, 3, 2 or 3, maybe cubic polynomial might work. Let's say I choose 2 knots here. All right, let's see what happens. Just for illustration, I choose 2 knots here. Here the choice of the knots is not so clear, but let me just choose these 2 knots for illustration. And I want a cubic polynomial, a cubic spline polynomial, to be continuous at these 2 knots. So that is my model here. The small box here is my one and only multiple linear regression model. And from here, you can split it into, you can write it as 3 separate models for the 3 segments. Here's your base model. In the middle segment, you add another one. And then here, you add one more for the 3rd segment. Okay? So, when I want to fit the multiple linear regression model, I need to calculate all the regressors. This one I know. And then I need to calculate this and this. Now if I can produce these 5 columns of numbers, I can use LM to fit it. And that's the idea. So let me just call this one X, this one X squared, X2, X3, X4, X5 for simplicity. I relabel them. And what is X? X is the time. X squared, square. X cubed, easy. So I can calculate the first 3. Now what about X4? X4 is this. If time minus 6.5 is less than 0, X4 will be 0. If X is more than 6.5, then X4 will be X minus 6.5 to the power 3. Okay? That's the idea. And similarly for X minus 13. So here's the R code to get X4 and X5. So what does that mean? That means, look at X. X is here. Okay. Hope this doesn't do anything. Now here is 6.5. Here's a knob. So if X is less than or equal to 6.5, that thing with a plus sign is 0. Otherwise it's X minus 7.0 minus 6.5 raised to the power 3. And so this is how I get this. Now for X2 terms, this will continue to be 0 until the next knob, which is 13. So the next knot is 13. So if it is less than 13 or equal to 13, it will be 0. But when it is more than 13, it will be 13.5. So how do I get this number? This will be 13.5 minus 13 raised to the power 3. That's how I get that. You get it? So, so the idea is to get all these regressor variables calculated. You can read this R program on your own. I think it's quite easy to understand. Basically, I just set a condition, if it is less than 6.5, I set it to be 0. Otherwise, I calculate xi minus 6.5 to the power 3. And so I got it. And then how do I fit the model? Very, very simple. Once I've calculated all my regressor variables, I can just fit a model. Put in a, you created all this, put it in a new data frame, and then you can fit the model. That model, I call it model.spline. Okay, well, plot the spline model on the data. So if you want to know how to do it, here's the R code for doing it. So when I fit this model, I can get all the regression coefficient. Yeah, and I can plot it on it. So this is the cubic spline model for the data. It looks like just one cubic model, but actually it comprises 3 cubic models. One for less than 6.5, another one in between 6.5 to 13, and then beyond. So it's a combination of 3 cubic models. So this, the next slide will show you clearly what I mean. So from here to here, the cubic model is defined by this, the base model. And from here, 6.5 to 13 is defined by this cubic model. And the last cubic model is defined by this, with the additional 2 terms. Now it looks very smooth, right? Because I want them to be continuous. This spline model ensures that they are continuous. If you fit 3 separate models, you are not going to get that. So this is, you can describe the whole model using this class notation, or if you are not comfortable with that, you can write it out. Okay? So the bottom line is we have one multiple linear regression model for the data. So how do we do tests? Well, if you have a multiple linear regression model, all the tests that we have described earlier will follow. For example, I want to test whether this spline model, is it useful or not? The entire spline model. So to do that, I test beta 1, beta 2, beta 3, 4, 5, all equal to 0. If they are all not significant, let's say, not significantly different from 0, then this spline model is useless. Now, if I reject the null hypothesis, then at least I know that maybe I need some of the terms. So you can do an ANOVA on the model spline that we have fitted, or you can, to test this hypothesis, you need to compare with a constant model, y against beta norm. So let's take a look. So what happened here is, to test the entire model, 5 degrees of freedom, p-value, which is very small, almost 0. So we conclude that the model is significant. In other words, there's evidence that the alternative hypothesis is true. After that, we go ahead and see which beta is different from 0. So we can do a model summary of the model. Well, take a look. X, X2, X3, X4, X5. They are all highly significant. Looks like we have found a significant model. Yeah, overall is significant. Everyone is significant. Looks good. That's why we have such a good fit. Can you see? Yeah? So it's not surprising. So what happened next? What happened next is I want to compare. So now I fitted a cubic spline model consisting of 3 cubic models in the 3 segments. And then we might want to ask ourselves, what about just a simple cubic model for the entire data set? Won't that work or not? Would that work? Because why do we want to have one model comprises 3 cubic model? Can I just use 1 cubic model? Okay, well, if you have that question, you are thinking in the right direction. Why do we want complication in life, right? When we can do a simple cubic model. And to do that, we simply test these two, whether we want them or not. We want to test beta 4, beta 5 equal to 0. If these two are 0, then model 1 is preferable. The simple cubic model is preferable. But when we test this hypothesis, we reject the null hypothesis, then the spline model is preferable. So we can compare. Now this is something that you cannot do if you fit 3 separate models. The naive approach, you can't do that. Only with one multiple linear regression model, we have the freedom to test whether a spline model is better or a simple cubic model is better. So here, I just compare the full model with the cubic model. That's how we do, right, in ANOVA. And this is a reduced model, this is a full model. The degree of freedom for testing beta 4 and beta 5 is 2. There are 2 betas. And the p-value is very small. What does that mean? That means there's strong evidence that we need the cubic spline model. Those 2 terms, beta 4 and beta 5, are significantly different from 0, or at least one of them. Then you can go and test which one, You can then test which one. So, if you are not convinced that a cubic spline model is better, here I plot 2 together for you to see. Here is a cubic spline model. Here is just a simple cubic model. What do you think? Which model fits the data better? That's the winner. Yeah? sometimes, we got too bogged down by testing beta 4, beta 5, and so on. Just draw a graph. It won't lie. It tell us the truth. See how bad the fit is for the cubic model. See? Not good enough. Yeah? So I hope with this example, you're convinced that why we need to go on to do cubic spline model instead of just a simple polynomial model. Yeah? Because we can improve the fit. And we are not giving up anything. We are still dealing with order polynomial. There's no added complexity except that, I have 3 cubic polynomials to describe each region. But they are all considered as one model. All right. As I mentioned earlier, if you impose the condition that the cubic spline model must be continuous at the knots, then the fit may not be too good sometimes. And can I fit a cubic spline model such that I allow for discontinuity? The answer is yes, I can. All I have to do is this. The difference is here. So, so what happened here is, suppose I have H knots. For every knot, I add this one. So this is a polynomial, also a cubic polynomial, but it starts from 0. It's x minus ti 0, x minus tj to the power 1, and so on. If I specify this way, it will allow for discontinuity. Well, in fact, this term here, beta I naught x minus t naught, from the part that I added, it forces a discontinuity at ti, at the knot. If this term is absent, then the model is continuous at ti. And this is what I've just said. The fewer continuity restriction required, the better is the fit, because more parameters are in the model. Yeah, you have less restriction. The more continuity restriction, the worse is the fit, but the smoother the final curve will be. Yeah. So let's study this cubic spline model with no continuity restriction. That means we allow for continuity with one knot. Here's the model that will allow for discontinuity. Here's the base model. Remember, now we only have one knot and there are 2 regions. This is the base model for the region on the left of the knot. Now, the other cubic polynomial, we add this term, 1, 2, 3, 4. We add these 4 terms to it. So what is the difference between this and the model that we described earlier? The difference is, for continuity, if you want the 2 to be continuous, you only add this term. This term alone. You get back the previous model. But if you want a continuity at the knot, you need to include this, and this. In fact, this is the one that you need to add. But we just want to have a cubic model here in x minus t. Well, so it may not be clear from the single multiple linear regression model. So let's write out the 2 models in the 2 segments, and then it becomes very clear. For x less than t, all those terms involving plus sign will be 0. So we have our base model here. Now for x greater than t, this plus sign says that this has to be x minus t, not 0 anymore, x minus t, x minus t. And what is beta 1 naught? What is x minus t to the power 0? Now if x is greater than t, then x minus t to the power of 0 is 1. So there's a 1 there. So there is a beta 1 because the x minus t to the power of 0 is 1. Now, look at these two equations. Are they discontinuous at the point t? Well, when x is t, you have all the x replaced by t. Now let's let x approaches t from the right hand side of t. So this will become 0. This will become 0. This will become 0 as x approaches t. What about this? This stays. So when x is very near t, the second model becomes just this. Now if you compare this and this, are they continuous? Obviously not, because there is a jump at the point x equal to t here. There's a jump of this magnitude, beta 1, 0. So if you define the model this way, you are going to get a model that is discontinuous. Okay? So that's what it is. And so if I want to test, for example, whether the two cubics model, are they continuous or not at the point, at the naught t, I can simply test this. Yeah, I test this term here, beta 1, 0. Is it 0? If it is 0, it means there's evidence of continuity at this point. So you can test some other things. You can test beta 1 naught and beta 1, 1. It will imply continuity of Sx and x prime x, and so on. And the last one, so these two you can take a look at yourself. Now this one, I will test beta 1 naught, beta 1, 1, beta 1, 2, beta 1, 3 equal to 0. So here, I'm trying to compare a single cubic polynomial versus a cubic spline model. So if beta 1 naught, beta 1, 1, beta 1, 2, 1, 3 is all equal to 0, that means I don't need these extra terms. A single cubic polynomial will be sufficient. Okay, so that's the difference. Okay, so here let me try and give you a summary of this. Okay, the first one, a cubic spline model with H knots and no continuity restriction. See, for every knot, I need to have I need to add a polynomial to it, starting with power 0, 1, 2, up to 3. So that's what I do for each of the knots. So what if I want to fit a linear spline model? It is a straight line model. So let's say I divide my segment into their h+1 segments, and I want to have linear, straight line for each segment. Well, that's easy. Change the cubic to a straight line. That's it. You change it to a straight line model. Here is, you add another straight line here. So you just change this quantity. So if I want a quadratic spline model, what should this number be? 2, right? This will also be 2. That will be a quadratic spline model. Now, let's look at a special case of this. Here, I have H knots. How about, let's just consider 1 knot. Maybe we can understand this pattern. Now, if I have only 1 knot, then there's only 1 T. There's only 1 T. And this sum, the inner sum, will be beta not 1, beta 1 knot and beta 1 1. So the inner sum, there are 2 terms. One is beta 1 knot, one is beta 1 1. Remember here, for this case, H is 1. So, the third one says we have a straight line model in each of the segments, and we allow for discontinuity. And this is what you will see here. So, that's the model. So if x is less than t, then I get the base model. Because this will be 0. This is 0. 0 to about 0 is defined 0. Remember that? And this is also 0. So for x less than the naught, I will have this equation here. This equation. A straight line model. Now, if x is greater than t, then this is a positive quantity. This is now a positive quantity. Raised to the power 0 is 1. And the other one is just x minus t to the power 1. Now, I can combine them together, all the constant term, all the x terms, and that would be my line here. And this is the discontinuity, beta 1 naught. Yeah? You see the similarity between cubic spline and linear spline? It's the same. Here I have one line here, described by the base model. Another line here, described by this. Okay, so let's see. Okay, let me just look at this one. Let's just compare this with the one that is continuous. Then I require my model to be continuous. So here I have H knots, and I want it to be continuous at the knots. So that's what happened. See, there's no double summation there. That's the difference. A linear spline model with H knots. A linear spline model with 1 knot and continuous. See, for continuous model, we have this. And when x approaches t from the right hand side, you can see that these two are the same. The two models are the same. That's why they are continuous. See, for x less than t, you have this model. For x greater than t, you have this model. See, when x approaches t from the right hand side, this part disappears. So there is no discontinuity at beta 1. And if you fit it, you get two lines. One with slope beta naught 1, another one with slope beta naught 1 plus beta 1. So that's what happened. Okay? So, in today's lecture for the first half, I've talked about how we can view a cubic spline model as one single multiple linear regression model. And that is good because all the theories, methods, whatever that we have learned in the past can continue to apply to this spline model. And is definitely much more flexible than the naive method of fitting cubic model in each segment separately. All right? And then the second thing that I talk about is looking at models that allow for discontinuity at the node. All right? And then in particular, we look at the linear spline model. Let's take 5 minutes break and then we'll continue from here. Well, I'm going to illustrate the fitting of a linear spline with one knot using the cholesterol age data that we have studied. So here is cholesterol versus age, and as you know, when you age, your cholesterol level will go up. And I think they might be, the data might behave slightly differently at this particular point, which I call a knot. Yeah? What did we do in the past? We fitted a quadratic model. So can I fit a linear model, a straight line model for both parts or not? Actually, there is one advantage in doing that. Because if you fit a quadratic model, eventually, you know, as you age further, your cholesterol level will go down, which is not true, right? At least if I fit a straight line model, my cholesterol level will go up and up until I reach the heaven. So that's what happened to everyone one day, right? Yeah. So, well, what do we want? Well, I am going to fit one that is continuous. So what happened here is, I am just going to add this term here. Just one term. I don't need the power to the power 0. If I add that term, it will force discontinuity at the point 35. So if I don't include that term, you know, x minus if I include this, then I force a discontinuity at the knot. If I don't, it will be continuous. So what happened here is you will have the base model here, base model for x less than t, and for x greater than t, you have another term involving x. So let's fit it. Now I'm going to skip this program, you can read it. The idea is we want to calculate this. Let's calculate this, which I call x2. I call this x2 here. So x2 is 0 if x is less than 35, but if it is more than 35, then I just look at the difference. So that's what the program does. And you can see the data here. For x less than 35, it will be 0, x2. Otherwise, it will just be the difference. After that, I fit the model. I got to put them in a new data frame so that I can use it. So here's my model, the spline model, linear spline model. And then determine all the coefficients. Now, here I'm just trying to plot it. Yeah, I'm not sure if my plotting skill is that good. Okay, but that's what I know. So when I plot it, that's what I get. I'm sure some of you are very proficient in R. You might be able to do better than me, but that's how I do it. So I have a line fitter here, the base model, and another straight line. It looks pretty good, right? At least it doesn't have the drawback of the quadratic model, which will, give you false hope that your cholesterol level will eventually go down after you pass age 80. You live forever. That model say you live forever. This model say eventually you will go to hell or heaven, I think. I think heaven is not going down, so it's going to heaven. So maybe better. I would like to go to heaven, not hell. Quadratic model say you go to hell. Okay, not so good. So, this is the test of the overall model. Beta 1, beta 2. Okay, beta 1, beta 2. We can test the overall model. It's highly significant. Yeah. So next is we can test, and then you can see that both are highly significant, both of parameters. So it looks like it's a good fit. And then you can also compare a simple linear straight line model and a linear spline model by comparing the additional term. So this beta 2 defines the spline model. Without beta 2, it's just a straight line model. And so here, I compare the straight line model, the simple straight line model with the linear spline model. And it's highly significant. It tells me that this spline model, linear spline model, is better than this. Obviously, you can see it's better, right? Look at how bad the fit is here. So, as I've said, you could still go to quadratic model, which will bring you to hell, or you will live with linear spline model, go to heaven. Your choice, okay? All right. So that is spline model. Now next, we'll go to something even more interesting. I'm excited. I think I have to keep going on because time is not on our side. This Deepavali holiday is coming, and it's going to take away 1 day of lecture from me. All right, parametric model. So, what we have done so far is called parametric model. Today we are going to learn non-parametric model. in particular non-parametric regression. And I'm going to tell you what is parametric, what is non-parametric, and what's the difference between them. And then we'll see how we can fit non-parametric model. And there are two types of non-parametric model that I'm going to discuss here. One is called non-parametric kernel regression model. Another one that I'm going to discuss is locally weighted regression model. Two. So two alternatives. Huh? Okay. What is a parametric model? Well, a parametric model is one based on parameters. What are the parameters? Beta 0, beta 1, beta 2. These are the parameters. So you can describe it using a parametric function. What is a non-parametric model? So here is an example of a non-parametric model. Again, I'm using the cholesterol H data. You can see it no longer follow any particular parametric model. It just changes with the data. So how do we get this? How do we get this? So here, I'm going to describe the basic idea behind a non-parametric regression model. Suppose I consider a point X here, and I want to find out how do I calculate this point here. If I know how to calculate this point, then I can calculate for another value of X, and so on. And then I join all these points together. That would be my non-parametric regression model. All right? So that's the idea. And so if I know how to calculate y tilde is the fitted value at the point X. If you understand how y tilde is calculated, you would have understood non-parametric regression. Alright, it's very simple. Everything is simple if you understand it, if not, it's very complex. Here's X. I consider a bandwidth. A bandwidth is just an interval enclosing the point. So I choose equal distance from X. And this interval, the enclosed X, has distance B. Yeah? So this B is called the bandwidth. Now, so what happens now is I will only consider all the points that fall within these 2 points, from here to here. I will only consider all those points that I have circled in blue. How many points are there? 1, 2, 3, 4, 5, 6. So there are 6 points that fall within an interval of X. And all those 6 points, they have different Y values, right? I will calculate the average of these 6 values. And the average of these 6 values will be this. You got it? So, the idea of non-parametric regression actually is very simple. If I want to calculate, let's say here, this point, I want to know what the value is. What I do is, I get a bandwidth of B, and then I locate all the points here that fall within this band surrounding X, and I calculate the average value of all this Y. That would be my fitted value for the non-parametric regression model. So at any X value, I will just calculate. So we can now see that, you can feel that, the filter value has to go along, it's greatly influenced by the Y values near this X, right? If they are high, it'll be high. If it's low, it'll be low. So it's actually adjusting itself according to the points that we have. So that's the idea. Well, here's a comparison of a parametric model and a non-parametric model. You can see the line is not very smooth because it is the average, of this Y value here. Sometimes if you have more there, you will, higher value at Y, it will move up. If there's a point that drop, then it might cause the line to come down. So that's the idea behind a non-parametric model. Well, you might already realize by now, the bandwidth has a big effect on the non-parametric model. If you choose a small bandwidth, you can see that the filter value will keep on changing, very sharply as you move along. But if you choose a very large bandwidth, suppose minus 1 million to 1 million, then you will get a horizontal line because all the points are always calculated. You see or not? So, very large bandwidth, not a good idea. Small bandwidth, it fluctuates too much. It's just like fitting a polynomial that passes through every point, And so you got to somehow choose a moderate bandwidth. And this can be done by visual inspection, actually. So now I'm going into the details of non-parametric regression, the mathematics of it. I have already described to you how I got this point. This point is based on the average of all the Y values within this band. So in a way, Y tilde is weighted, it's just a sum of Wj times Yj. So for all the points here, Wj will be 0. Okay? There's no weight. So all these points here, Wj will be 0. But for all the points here, this Wj will be 1. So k is a binary function. So k means if a point falls within the bandwidth, then this quantity here will be 1. So in other words, every point here, this is 1. So if there are 6 points, the denominator here will be 6. And then the weight will be 1/6 for each of these Y value. So that's what it is. And so this is the mathematics that describes how you find the average of all these Y values at a particular X value. Using this notation here, K. And so you can go home and think about this. All right. So here, of course, if a point falls outside, this K is 0. Yeah. So for this particular example, if you sum up all the data points, there are only 6 values that are 1. And for each of these, the K is 1. outside is 0. So that's a non-parametric regression. And how do you do it using R? You know, the theory is very beautiful. I actually quite like non-parametric regression. It follows the data. But it's useless if you don't know how to do it. Fortunately, there is a way to do it. So here I just fit a parametric regression model. This is easy. How to draw it, you can figure that out. But how do you fit non-parametric? Yeah. Well, good news. There is a function in R that will allow us to do that. It's called NPREG. It's not LM. LM is for parametric regression model. But, you know, but for non-parametric regression, you use this. So what if I say in the exam, you know, write down the code for fitting a non-parametric regression model. Can you do that? At least copy down this formula, right? Yeah? Whatever I ask you today won't come out anymore, okay? But you can get some idea. Well, I hope you don't learn this by copying down the formula. You learn it because you try out using R. You don't even need to remember it. And here's the model, cholesterol versus age. And the weighting, I use a Gaussian, which I will explain a little bit later. Yeah? And then this is the bandwidth. So I can do that. And I have a multiple linear regression model fitted. So it is quite easy if you have this function. Yeah. And what if I change the bandwidth to 0.5? You can see that, you know, it fluctuates a lot more now. It tries to follow every data point closely. So not too good. I think bandwidth of 2 in this case is the best. If you try a bandwidth of 6, it's even worse. The line will become more and more horizontal. Yeah? Try a bigger bandwidth and you'll get this line for it. Okay. Now, the kernel function that I have, the weighting is defined by this function called KT. KT is called a kernel function. Now the first one is what I have described. So if I have x here, and let's say x plus c, x minus c. Now, the one that we have studied is this. Any point outside, kt will be 0. Here, kt will be 1. Here, kt will be 0. Okay, for that. That means if any point, for example, the 6 points falling within the band, right? So I have a weight, total weight of 6. And every point inside there will be 1. Now, this is called a box weighting function. It's just equal weight. But you could also give a weight of this kind. You can give it a weight of this kind. here's x. What that means is, anything outside, kt is still 0. Kt is 0. But inside, I'm not talking about the triangular kernel function. Inside, if it is close to C or exactly at C, the weight given to that observation in calculating the average of y will be the largest. And if it is further out from x, let's say here, then the weight drops to this point. So the weight here is the highest. If it moves further out from x, the weight will drop. That's why it's called triangular. Now normal is this case. Normal is this particular weight. This one is this. So it's just a bit smoother than the triangular version. And the one that I used is called Gaussian, right? Well, that is called normal. Gaussian is another name for normal. So, well, look at this sentence here. The properties of the kernel smoother depend much more on the choice of the bandwidth than the actual kernel function. So, what that means is, when you fit a non-parametric regression model, what really counts is the bandwidth, not so much what kernel function you use. It is the bandwidth that is the more dominant factor in affecting the final non-parametric regression model that you will get. So it doesn't matter. Because of that, I would choose whatever kernel function, for use. So in today's lecture, second part of it, I have described what is a parametric model, what is a non-parametric model. There's no model to describe it. And then, non-parametric tends to follow the data. It is completely controlled by the data, in a way. Parametric is just a smooth curve. Yeah? So, effect of bandwidth, I've talked about it. And what is a non-parametric kernel? It's based on the average of all the y's within the band. And then I talk about the R program for fitting parametric, non-parametric, and kernel function. So I guess I will continue with this Monday. So let's have 5 minutes for the quiz.
Find sheets somewhere there, like somebody read it. I still don't understand this. What's this function of WDA?
Not showing up, 1 minute. Maybe I need to access it using my
This term is just the
PDF.
the difference in the difference. This is SSX QA, and then this is for the individual one. So this is your contribution to the total value of W. So this is your weightage based on how
Something
many
is
other.
wrong with my
Your weightage of how much
I guess I will
your
figure later.
value affects the predictor Y based on how many other points are there. So the more points there are, the higher this value will be, the less your own weightage will be.
Okay, can you all read it? Alright, when you're done, you can go.
No.
I'm going to open up a quiz for you to answer.
0, 1, 2. 0 and 2.
Okay, done.
What's the STI? Beta not term. So the beta not term will force it to be If only it tested this theory terms instead of
You put Wk9 as well.
that would be, I forgot what I did quiz here.
What if canvas just died? I can't leave the quiz. Why does it easy? This is
Wait. Okay, wait.
no, you're right. You're right.
No, you tried to read it. I is equal to Y. I doesn't.
No, I is
I is the. What matters is the power of this thing. How many span knots there are? There are 2 knots. And each one is a full quadratic. What do you mean? Okay, so this is what X is the value that you want to predict. So like you X is the given value. I said I want to predict value at X. Xj is Xj and Xk are basically all the samples within this technically it's all the samples, but because of K, right, the only one that matters are the ones within here. Because anything that's not within this band is just 0, and then it doesn't contribute out. So this is just the summation of the distance.
So I have an X I put here, then because this is summation of n of all wj's. So I will take all of these, and all of these will naturally give me 0. This one will give me all 0. But here it will be 1.
And then over the value also the value of everything. So
okay,
essentially you're weighting your own
weighting
your own Y's contribution based on the other Y's relative. Like the distance between the other samples. Which doesn't make sense. I thought it would have a higher weight with closer, but this looks like it has a higher weight with further.
No, these are all equal weight.
No, because this value will be greater. X minus X will be greater than
Yeah,
whatever
but
you are.
because K will just transform into 1.
Oh.
Yeah, so it's a count lah. It's an average count.